All right, this is the solutions to homework number 2. The first question was exercise 2.1, where we were asked to plot enough points to sketch a complete graph of several different functions, and then locate where the function is increasing and or decreasing, and also find local and global maxima and minima. Okay, so the first one is the function y equals 3x minus 2. And this one's pretty straightforward to graph because it's just the equation of a straight line, right? Y equals mx plus b, where m is the slope and b is the y-intercept. So I don't even really have to plot any points. Although I suppose I could if I really needed to. Okay, so we've got our x-axis and our y-axis, right? And the intercept is -2, and the slope is 3. So I'll go up 3 and over 1. And I could even do that one more time. 1, 2, 3, and over 1. So there we go. Not very good at drawing a straight line, apparently. Okay, but there we go. There's our line and our graph. It's increasing everywhere. I'll say over entire domain, which is the set of real numbers, right? It's not decreasing anywhere, and there's no maxima or minima, so no local or global max or min. All right, the second one is y equals -2x. So same thing. This is just the equation of a line, right? I'll just put a +0 here so that you see that the intercept is 0, the y-intercept is 0, and it has a slope of -2. So try not to take up so much space. I don't need this much space here. But and I won't bother labeling anything just for the sake of time. All right, so the y-intercept is 0, and it has a slope of -2. So we'll go down 2 and over 1. There's 1 point. I'll go down 2 more and over 1 more to get a third point, even though that's not even really necessary. And there is our line. Okay, so it's decreasing on the entire domain, the set of real numbers, and again, no local or global max or min. All right, the third equation is y equals x squared plus 1. Now I know that this is the graph of a parabola with y-intercept equal to 1. But I'll go ahead and just pick a few points to illustrate. So when x is 0, y is 1. So there's 1 point. Let's pick another point. X is 1. Well, 1 squared is 1, plus 1 is 2. And it's the same thing for -1, right? If x is -1, then we plug that in. -1 squared is just 1, plus 1 is 2 again. So there we go. And it's going to continue like that. I could plot some more, but you should have had something that looks like that, the parabola. Okay, so let's see. I'll start with decreasing, actually. Go from -infinity to +infinity. So decreasing on the interval negative infinity to 0 and increasing on the interval 0 to positive infinity. And let's see, there's a local and global max, or I'm sorry, min at the point, let's see, 0, 1, and there are no local or global maxima. Okay, the fourth equation is y equals x cubed plus x. So this is more difficult. I don't know right off the bat what this looks like, but I can guess that it's going to have an S shape based on this cubed, x cubed. So that's my guess. So let's just plot some points and see what it looks like. So I'll just start with x equals 0. Well, then y would equal 0. So this is going to go through the origin. If I pick 1, x equals 1, then I will get 1 plus 1. So if x equals 1, I get 2. If I pick x equals 2, I get 2 cubed, which is 8, plus 2 is 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I got a point way up here, and it's just going to explode upwards from there. So let's pick some negative numbers. So let's do -1. So -1 cubed is just -1, plus another -1 is -2. So there we go. If I pick -2, we're going to get -2 cubed, which is -8, plus a -2 is -10. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Somewhere around there. All right, and this is just going to, fall extremely fast downwards. So like I said, it's going to have kind of an S shape like this. So it's increasing everywhere. It's not there's nowhere that it's decreasing. And there's no global or local max or min here, right? So you'll notice that if it's increasing or decreasing on the entire domain, we're always going to get this, right? There's no global max or global min. Let's see. Equation 5 is y equals x cubed minus x. Okay, so this is probably also going to have sort of an S shape, I'm guessing, but let's find out. Okay, so we'll start at the origin. That's just 0. If x is 0, then y is 0, so that'll go through the origin. If x is 1, we get 1 cubed is 1 minus 1, so there we have 0 again. Okay, so we might want to pick something in between 0 and 1 just to see what's going on there. Maybe 0.5, so let's try x equals 0.5. X cubed in that case is going to be 0.125 minus, and then we subtract x. Let me not do it that way. Let me just say y. There we go. So that's right there is x cubed, and then we need to subtract x, which is 0.5, and that equals a negative number. Let's see, what is that exactly? That's negative 0.875, I think. No, that's not right. I think it's 4 or 375. That's what it is. negative 0.375. So we do have and if that's 1, we got a little dip there, okay? So that's interesting. Let's see what happens when we pick 2. We get 8 minus 2, which is 6. So 1, 2, 3, 4, 5, 6. Okay, so I think we are going to have a little dip there, and then that's going to go up like that. And we're probably going to have something similar on the other side. So let's pick negative 1. That's going to be negative 1 minus negative 1, so 0 again. And then if we picked instead negative 0.5, we would basically get positive 3.75, which is going to be kind of right there. Okay. And if we did negative 2, we would get negative 6. So 1, 2, 3, 4, 5, 6. All right. Now, I'm not 100% sure that this positive 0.5 and negative 0.5 for x, I'm not sure that those are mins and maxes. And without using calculus, I'm actually not too sure what would be the best way of figuring out those specific maxes and mins here, this max and this min. But it definitely there's a max somewhere in this range between negative 1 and 0, and a minimum but somewhere between 0 and 1. Now, of course, they're local. But at the very least, let's see, how could we figure this out graphically? I guess we could zoom in here and just try all kinds of different values between 0 and 1. But I'm guessing that since the graph crosses the x-axis at 0, negative 1, and positive 1, I'm guessing that the max and min is halfway between those intervals. So this is probably going to give us the min, right? This would be the x value of the min, and this would be the y value here. And then negative 0.5 and positive 0.375 for the max here. So, if you can't figure out the min and max by graphing, don't worry too much. That's going to be hard for a lot of different possible equations. So, but you should at least be able to identify that there is a global max somewhere in this range and a global min somewhere in this range here. But at the very least, let's see. So if this is in fact well, this would be the min, and x equals negative 0.5, y equals 0.375, that would be the max, and these are local, right? Then we would say that it's increasing on the interval negative infinity to negative 0.5. Then it's decreasing on the interval negative 0.5 to 0.5. And then it is again increasing on the interval 0.5 to positive infinity. And no global max or min, but there is a local max on the interval negative 1 to 0, and there's a local min somewhere on the interval 0 to positive 1. So that would be sufficient for this problem. And then the last one, equation 6, is y equals the absolute value of x. We saw this one in class, right? This one's pretty straightforward. It's basically just a v. That would be, all right, that would be a line with slope negative 1. And then this would be a line with slope positive 1. And so let's see, it's decreasing on the interval -infinity to 0 and increasing on the interval 0 to +infinity. And there is a global min at the point 0, 0. That's technically also a local min, right? So I'll say local and global min. There's no global max or local max, right? Because these just continue to get higher and higher. So, all right, there you go. There's the solutions for the first problem, exercise 2.1. All right, the next problem was exercise 2.4. And we are asked to determine the domain of several functions. The first is y equals 1 over x minus 1. So the only restriction here is that this denominator can't equal 0. So x cannot equal 0. I'm sorry, x cannot equal 1, right? Because if x was 1, the denominator would be 0. Okay, so x cannot equal 1, but everywhere else, every other x, it's defined. So the domain in this case is defined as the set of x's that are elements of the set of real numbers such that x does not equal 1. All right, so there's the domain of that one. The second equation is, well, I guess they're lettering these, so this is A and this is B. The second equation, B, is y equals 1 over the square root of x minus 1. So here we have a few more restrictions, right? The first, again, is that the denominator cannot equal 0, so x cannot equal 1, once again. And we also can't take the square root of any negative numbers. So in fact, x has to be greater than 1, in fact, right? So there we go. That's actually the domain right there. So in set notation, let's see, we'll just do that. X's that are elements of the real set of real numbers. Oops, I should have put a colon here, not a comma, right? Such that x is greater than 1. All right. And again, it can't be equal to 1, so this is a strict inequality. All right. Equation C is y equals 1 over the square root of x squared plus 1. And there's really no restrictions here. There's no choice of x that would make this 0, and there's also no choice of x that would make this negative. So in fact, here the domain is defined as all x's that are within the set of real numbers such that, oh wait, that's it, because there's no restrictions, right? There we go, so we're done. Equation D is y equals 1 over, x over x squared minus 1. And again, we just can't have a 0 here in the denominator, so the only value of x that wouldn't work is, well, actually there's two values that wouldn't work. X cannot equal 1, and it can also not equal -1. So the domain is all x's that are elements of the set of real numbers such that x does not equal 1 and x does not equal -1. Okay, that's the only restrictions on that equation there. All right, equation E is y equals the square root of 1 minus x squared. Okay, so the only restriction here is that we cannot take a square root of a negative number, which means that, let's see, a lot of numbers aren't going to work for this one, in fact. So basically, whatever the value of x squared is, it has to be less than 1, less than or equal to 1, right? So in other words, x squared has to be less than or equal to 1. Anything bigger than that would give us a negative number. Okay, so let's see here. How do we evaluate this? Can't just take the square root of both sides, unfortunately. Let's see, x squared less than or equal to negative 1. That's basically going to be anything in the range of this interval. Let's see, I'll put it this way. X is an element of let's see, negative 1 to 1. Right? Pick anything smaller than negative 1, say negative 2. You plug that in here, you'd get 4. So 1 minus 4, that's a negative number. That wouldn't work. And that would be true for anything less than negative 1. And same for anything greater than positive 1. So this is our domain right here, right? So in set notation, let's see, x is an element. We can put it this way, in fact. X is an element of the interval negative 1 to 1. And in fact, that would be a closed bracket because it could be equal to negative 1 or positive 1. So negative 1 included and positive 1 included as well. So not an open bracket like this, but rather a closed bracket to indicate that these are included in the set, right? So there we go. And the last one, equation F, y equals 1 over the square root of 1 minus x squared minus 1. So this, you'll notice that this isn't under the square root sign there. So basically what that means, again, we just can't have 0 in the denominator here. So that means that the square root of the square root of 1 minus x squared cannot equal 1. Well, what are things under the square root here that would give us 1? Just 1. So in other words, 1 minus x squared cannot equal 1. Which means that, let's see, let's move this over here and move this over to the right-hand side. So in other words, x squared cannot equal 0, which simply implies that x cannot equal 0. All right, so there we go. All real numbers except for x equals 0. So the domain, I don't know if you saw that. Maybe that was missing there, but right, just did some algebra to figure out what x squared could not be, right? And therefore, x squared cannot be 0, which means that x can't be 0. Pretty straightforward. So the domain is the set of x's, which are elements of the set of real numbers, such that x does not equal 0. All right, there you go. All right, the next problem was exercise 2.8, which just asks us to find the formula for various linear functions. So just the graph of a line. So this should hopefully be pretty straightforward for y'all. So the first one is a line that has slope 2 and y-intercept. I'll go ahead and write this. Slope 2, y-intercept at the point 0, 3. Okay, so, I mean, that's always, the x value is always going to be 0 if it's the y-intercept. So that's kind of redundant information there. But just using our equation of a line, y equals mx plus b, where m is the slope, and b is the y-intercept, this is pretty straightforward. It's just y equals 2x plus 3, right? There's the y-intercept there. All right, so there you go. There's the first one. We're going to use this over and over again. B, for part B, it's slope -3 and y-intercept at the point 0, 0. And so our equation is going to be y equals -3x plus 0, right? So I don't have to write that out, but there's a plus 0 there, right? So there you go. There's B. C, slope is 4. And this time they don't tell us the y-intercept. They just tell us another point that this line goes through. Goes through the point 1, 1. All right, so we can start off with this at least, right? We know that much. And the question is, what's the y-intercept? So there's a couple different ways you could do this. Let's see here. Basically, probably the easiest way to do this is plug this in for x, right? So what we're looking for is b here, so I'll leave it as a variable, right? So let's plug this value in for x. That gives us y equals 4 times 1 is just 4, plus b. And I guess I could have gone ahead and plugged this in for y as well. Okay, there we go. And now we just need to solve for the unknown y-intercept. So that's pretty straightforward. And that gives us b, I'll leave it over here, b equals -3. So our final equation is y equals 4x minus 3. Sorry if you didn't see that, but right. So again, we know the slope is 4, so we can start with this, and this is an unknown, right? That's what we're looking for. So I just called it b, since that's what we call it in our general equation of a line. And then I plugged in this point, 1 for x and 1 for y. So I put 1 here for y. I plugged in 1 for x, and 4 times 1 is just 4. So we get this equation here with just a single unknown that we can easily solve for. Subtract 4 from both sides, and we're left with b equals -3. That's our intercept. So there's our final equation for that one. All right, for D, has a slope of -2 and goes through the point 2, -2. So we're basically just going to do the same thing we just did. Start off with y equals -2x plus b. We don't know what b is. We need to find it. And so we just plug this in for x and this in for y, and we get -2 for y equals, let's see, -2 times 2 is -4 plus b. And there we go. We can solve for b now. So I'll add 4 to both sides. And we get that b equals 2. And so our equation is y equals -2x plus 2. Okay, E. All right, so now we're getting a little trickier here. E goes through 2, 3, and 4, 5. So I'm going to start by using these points to figure out the slope, right? So remember that slope is rise over run. Okay, so the rise, of course, is the change in the y value. So we go from 3 to 5. So the rise is 2. And the run is also 2, right? We go from 2 to 4. Okay, so the slope here is just 1. And then we just continue doing what we had before. So I'll write those points again, 2, 3, and 4, 5. And the slope is 1, as we just calculated. So y is going to equal to 1 times x, or just x, plus b. And then we can pick either of these points to plug in for values of x and y to find out what b is. So I'm just going to use this one. So the x value is 2, the y value is 3. So we get 3 equals 2 plus b. And now we can solve for b. And we get that b equals 1. All right, so our slope is 1, our y-intercept is 1. So there you go. Y equals x plus 1. And the last one, f, goes through the points 2, -4, and 0, 3. So again, we're just going to find the slope, which is rise over run. Let's see, so the rise, start with the y value, right? That's the change in the y value. So we're going from -4 to 3. That's a rise of 7. And the run, we're going from 2 to 0. So that's a negative run, right? That's -2. So there's our slope. Okay, so we'll start constructing our equation here. -7 halves x plus b. And then again, we're just going to pick either of these points to plug in values for x and y. I'll go ahead and use this one. So we get -4 for y. That equals -7 halves times 2. All right, and those will just cancel out, and that'll become -7 plus b. And then we can solve for b. So I'll add 7 to both sides. That gives us 3 over here, and that's the y-intercept. So for this one, our equation is y equals -7 halves x plus 3. All right, the next problem was exercise 2.10. Let me find it here. Okay, and there's 2 parts to this. The first part says, use the geometric definition of the derivative to prove that the derivative of a constant function is 0 everywhere, and the derivative of f of x equals mx. So let me just write this out. So I'll just say prove geometrically, which is to say with a graph. Geometrically, the geometric definition of a derivative, that the derivative of a constant function is 0 everywhere, and the derivative of f of x equals mx is f prime of x equals m for all x. All right, and this is very straightforward, right? In fact, I'm going to do it without even using a graph. So the derivative of a constant function. So that's just some f of x equals some constant b. We'll call it b, in fact, right? And keep in mind that y equals f of x equals b. Okay, so remember that the derivative of a function is just its slope. And here, right, if this is the slope of a line, another way of writing this would be y equals 0x plus b for any constant b. And there's our slope, right? It's 0. And that doesn't matter what x is. That's everywhere, right? So that one's pretty straightforward. And so is the next one, in fact. So if y equals f of x, which equals mx, another way of writing that is simply y equals mx plus b, where m is the slope, and that's exactly what the derivative is. It's telling us the slope of a line, and the slope of this line is m everywhere, or in other words, for all x. So that's all you really had to do. Suppose you could have drawn, graphical examples of these, right? Picked some value for b and drawn that in a graph, and shown that its slope is 0 by picking 2 points on it and calculating the slope, and similarly for this here. But that's really all you have to do. Right, I guess, you should add slope is 0 everywhere, and slope is m everywhere. So I guess I'll put for all x, right? Everywhere for all x. So that one's pretty straightforward. B says, use the method of the proof of theorem 2.2 to prove that the derivative of x cubed is 3x squared and the derivative of x to the fourth is 4x cubed. So let me go back to theorem 2.2 here just to make sure. Okay, so this is basically, let's see, there's a proof here somewhere. Okay, so basically we're going to use our limiting exercise. So remember, right, slope is rise over run. And if our function is x cubed, f of x equals x cubed, we're basically going to have, right, we basically want to pick 2 points. So one point could just be x cubed, and another point would be f of x plus h equals x plus h cubed. So if we're talking about the rise, right, the rise is going to be equal to, doesn't really matter what order you do this in, you just have to be consistent. So we'll do f of x plus h, not b, h, minus f of x over, let's see, I got to be consistent here. So x plus h minus x. And I'm going to rewrite this. Instead of using the function, I'm going to actually use, right, instead of using the function notation, I'm going to use the function itself. So here we've got, let's see, we've got x plus h cubed minus x cubed over x plus h minus x. And this can simplify, right? The bottom is easily simplified. Those are going to cancel each other out. And then let's see if we can, let's expand this, right? So that we can maybe simplify the top. So I'll start by putting it this way. Right, there's x plus h cubed. And then I'll go ahead and simplify the bottom here. We're just left with h on the bottom. Now let's expand on this, right? So this will be a little bit of review from high school. So let's see, x times x is x squared, plus x times h is xh, and then h times x is, again, xh, and then h times h is h squared. So I expanded the first two here. We still have another x plus h here, minus x cubed, all over h. And of course, we could simplify this to, right, just make that 2xh. So I'll go ahead and write that actually, because that'll be helpful when expanding it again. So x squared plus 2xh plus h squared times x plus h minus x cubed all over h. All right, and then we just need to expand again. So it's going to be lengthy, but we'll go through it here. So x squared times x is x cubed. X squared times h is x squared h. I did those two. Now I'm going to start with the middle term and do the same thing. So 2xh times x is 2x squared h. 2xh times h is 2xh squared. All right, and then just the last term to do here, h squared times x is h squared x. Let me keep my terms consistent. I'll always keep the x's before the h's just to be consistent here. Let's see. So let me do that again. H squared times x is x h squared, and then h squared times h is h cubed. And then we have, so that's fully expanded now, and we have minus x cubed, of course, there, and that's all over h. And then let's simplify this. So let's see here. We've got an x squared h here. We've got two of them there. So that'll be 3x squared h. So x cubed plus 3x squared h. So we've taken care of those. We've got an xh squared here, two of them, and another one. So 3xh squared. And so we've taken care of those. We've got a plus h cubed and a minus x cubed here, which actually would cancel out with this one. So I'm just going to go ahead and erase that. Okay, so that's the simplified version there, all over h. And you'll notice that h is in each of these terms, so this will actually cancel out with that. One of these h's, so that'll become 1, and one of these h's, so that'll become 2. And so what we're left with is 3x squared plus 3xh plus h squared. Okay, so there's our simplification. And we just need to take the limit as h goes to 0. Well, as h goes to 0, that becomes 0, that becomes 0, and all we are left with. All right, I guess technically, let me be clear here. The limit as h goes to 0 of this thing will simply be 3x squared, which is exactly what we were trying to prove. All right, there you go. All right, this is the solution to problem 2.14. And it basically states that using theorem 2.3, we proved that the derivative of y equals k to the x to the k power is k times x to the k minus 1 for all positive integers k. And the exercise is asking us to use the quotient rule, right? So here's the quotient rule. Right, so if we have one function divided by another function, the derivative of that with respect to x naught, whoops, the derivative of that with respect to x naught is equal to the derivative of f with respect to x naught times g of x naught minus f of x naught times the derivative of g with respect to x naught divided by g of x naught squared. And we're asked to use this quotient rule to extend this result here to values of k that are negative, right? Negative values of k. So if we have a function f of x equals x to the k power, where k is negative, another way of writing that is we have f of x equals 1 over x to the negative k power. Okay, so we have a quotient here. Basically, in this quotient, x to the negative k power is going to be g, and f of x is just equal to 1, right? So I'm going to say let, and hopefully this isn't too confusing since I'm using now a different f. So maybe I'll change this to some other letter just to be clear here. So let's see, what's a good letter? H. Let's use H. Okay, so let's say that H of x equals 1. Okay, so we're going to let that be f in this case here. And g of x equal x to the negative k power. All right. Now we can use the quotient rule to prove that the derivative of this, right, when k is negative, is going to be the same result we have here. Okay, so we're going to use the quotient rule. So in this case, right, we need the derivative of h, right, because now we're using h instead of x, just to be clear, differentiated from this function. So we need the derivative of h of x, which is just 0. So let's see here. I'll write this out a little bit more explicitly. There we go. Okay, so that's going to be equal to the derivative of h of x, which is just 0. So, it doesn't matter what g of x is, that's just going to be 0, so I'll just leave it as 0, minus g of x for us here, right? I'm sorry, h of x. So we've got h on top there. H of x, which is just 1, times the derivative of g of x, which will simply be negative k times x to the negative k minus 1 power. And that will all be divided by g of x squared. So square this thing. So I'll put, I'll do it like this, right? Okay, so let's simplify that. That just disappears. We've got a negative times a negative, which is a positive, so that'll be positive. K x. Now I'm gonna take the negative out of here. Okay, and then divide that by x to the k power squared. And that can simplify to this. And now we have x's here and here with exponents. And so we can basically just subtract negative 2k from this one. So basically what this simplifies to is k times x to the negative 1. Maybe this was actually pointless, but we'll see. Negative 1 times k plus 1 minus a negative 2k. And we can simplify this. So actually, yeah, this was kind of pointless, actually. I thought it might be useful, but this is going to be equal to k times x to the negative k or minus k minus 1, and then minus a negative is plus, so plus 2k. And that simplifies to k times x. We've got a 2k minus k, so we have just 1k left over, and minus 1. Okay, which is exactly the same result that we had up here. So we use the quotient rule to prove that this is true even for negative values of k. All right, here's the solution to exercise 2.16, where we are given various functions that are piecewise, and we are asked to sketch the graph of each and describe whether it is continuous and or differentiable at the point of transition of its two formulas. So where does the piecewise function split, in other words? So let's just take a look at the first one here. We've got y equals positive x squared when x is greater than or equal to 0, and negative x squared when x is less than 0. All right, so let's go ahead and sketch its graph. So I'm going to start with the top one, pick some values of x. I'll start with 0. So when x is 0, y is 0. Okay, so this is going to go through the origin, or at least start at the origin. We don't necessarily know if it's going to go through it yet. And then I'll pick another positive x value, say 1. 1 squared is just 1. 2, x is 2, we get 4. Okay, so on the positive x, for the positive x values, right, the domain of positive x's, or the part of the domain where x is positive, there we go, that's probably the best way to say it. We basically just have half of a parabola. All right. Now let's do the next one here, negative x squared for x less than 0. Now I know it doesn't say equals here, but let's just plug in 0 anyway. We get 0, right? But we don't have the equality here. So let's pick a value that's really, really, really close to 0, maybe 0.000001. Well, that's just going to be a negative number that's really close to 0. So this is actually going to end up being continuous. And let's pick another negative number. Let's pick negative 1. Negative 1 squared is 1, and negative x squared is going to be negative 1. If x is negative 2, we get 4, negative 4. Okay, so we basically just get sort of the same picture that we got on the right side on the left, just, kind of flipped down, I guess. All right, so this is definitely continuous. And it's differentiable, right? It's smooth. There are no kinks in it. Okay, let's take a look at B. Y equals positive x squared plus 1 for x greater than or equal to 0. And negative x squared minus 1 for x strictly negative. All right, so let's see. We're going to have another parabola here with y-intercept 1. I can tell you that right off the bat. But let's go ahead and start this first part with x equal to 0. When x equals 0, y equals 1. Okay, so like I said, that's our x-intercept, or our y-intercept, rather. If I pick x equal to 1, we get 1 squared plus 1, which is 2. If I pick x equal to 2, we get x squared is 4 plus 1 is 5. So 1, 2, 3, 4, 5. Okay, so again, we basically get a parabola. It's just been shifted up by 1. All right, and then again, I'm going to, even though we don't have an equality here, I'm going to think about what this would be if x is 0. And if x is 0, you can almost think of it like a limiting approach, right? As x approaches 0 from the negative side, this basically, we can basically just plug in 0 here, and then we have minus 1. All right. So looks like this is going to be discontinuous, right? It's not going to be continuous. Now let's go ahead and pick some values for x. We'll start with negative 1. Negative 1 squared is 1. So that's minus 1, which is negative 2. If x equals negative 2, we get x squared is 4, and we get minus 4 minus 1, which is negative 5. So 1, 2, 3, 4, 5. And again, we get something that looks, like half of a parabola, but we do have a discontinuity here. So this one is not continuous. And it's not fully differentiable, therefore. It is differentiable on subsets of the domain, right? So I'll say is differentiable on R minus minus. Okay, and actually, to be a little bit more specific with my graph here, I should have made this dot an open circle to indicate that that point is not part of that side of the function. But this function is differentiable when x is strictly negative and is differentiable on R plus, right? Non-negative numbers. So that'd be from here onward. But it's not differentiable everywhere, right? So because of the discontinuity. All right, let's take a look at C now. For C, we get y equals x cubed when x is less than or equal to 1, and is simply x when x is positive, strictly positive. All right, so let's graph this. All right, so I'll start with x equals 1. When x equals 1, x cubed also equals 1. So we've got a point here. Now we're doing values less than or equal to 1. So now I'm going to go to 0. X equals 0. Well, that's just 0. Y equals 0. When x equals negative 1, x cubed. So negative 1 cubed is just negative 1. Let's see here. We'll go one more. When x is equal to negative 2, this will be negative 8. So 1, 2, 3, 4, 5, 6, 7, 8. Okay. So as we can see, it kind of has that standard cubic shape here. It is going to curve that way and then curve back up as it comes to this point. All right, and then for x is greater than 1, we can kind of use the same process we were doing up here. Let's assume that x approaches 1 from the right, so it's becoming smaller and smaller, closer to 1. In that case, we'd get x equals 1, which is right there. So that's good. It looks like this is going to be continuous. And then this is just, a straight line whenever x is greater than 1. So when x is 2, y is 2. When x is 3, y is 3. And we just get a straight line from that point. Okay, so this is continuous. But there is a kink here, which means it's not going to be differentiable at that point. So I'll say it is continuous And it is differentiable except at this value of x equals 1. Right, so it's differentiable everywhere else because it is smooth, except for at that point right there. There's a little kink in there, and it's hard to see that there's a kink there. The way I've drawn it, it's pretty small. But if you plugged this into a nice graphing tool, on the internet or something, and you could zoom in there, you would see that there's a kink there. So it's not smooth at that point. All right, and the last one, D, y equals x cubed when x is less than 1, and it is 3x minus 2 when x is greater than or equal to 1. Okay, so let's sketch this one out. Start with x equals 1. So we can, again, think about the limiting approach here. So as x approaches 1 from the left side, so it's getting bigger and closer to 1, this number is getting closer and closer to 1 itself. So there we go. Of course, it's not included, though, so that's why the open dot there. It's strict inequality. And then let's pick some other values of x less than 1. So 0, that'll be 0. Negative 1 will be negative 1. Negative 2 would be negative 8. Okay, so again, we get that sort of cubic shape on one side there. And then let's pick some values of x greater than 1. Greater than or equal to 1. So when x equals 1, we get 3 minus 2, which is just 1. So that point will be filled now. So this is going to be continuous. For x equal to 2, we get 6 minus 2, which is 4. And this is just a straight line, right? So from this point on, it's just a straight line. So again, we do have continuous, but there will be a kink right there, which means it's differentiable everywhere except for at x equals 1. So continuous and differentiable except when x equals 1.